Hello, everyone. I don't know who we've got in remote, but hello, hello, hello. And today we have the marvelous king of the underworld, Chris Heckman. I was going to say Pluto or Hades, but
Hades,
you know, the king of the subterranean caverns and award-winning part-time Amazon employee, Chris Heckman.
Thank you, Mark. Yeah. Oh, thank you. Yeah. I know actually that the applause was for the introduction, not for the speaker. So yeah, today, you know, I was thinking we could have a pretty informal conversation about debriefing what happened at the Subterranean Challenge event that just concluded last month. And I'm going to give you first a quick brief overview of our team, then I'm going to talk about the challenge itself, and then I'm going to go into a few different areas of research that we conducted as a team into field robotics in order to have a successful deployment at this Marble event or this final event. And then where I think things are going after this and some challenges that still exist. So we had a huge team. This was a $4.5 million project over 3 years, funded by DARPA to be able to support subterranean exploration. And I need to give credit to the team first. We sort of broke the team loosely across different boundaries of efforts, and those are efforts that I'll describe today. You'll see that almost all of us were present at CU, a very different team composition than other teams, which tended to be broken maybe in half, one institution, another institution. You know, we were almost like 95% CU, at least at some point. And in red, I have all the members of my research group, either at some point during the project or, you know, still as a member of my research group. I didn't break out the undergraduate students explicitly, but you'll see that there are about a third of the team is made up of undergraduate students. And that was a real benefit to us. And, you know, we had people graduate and everything during the project, but these are people the people on this slide are people who really gave, you know, almost at least 2 years of their life to this project. And it was we were very much, you know, we were nothing if not for our people. So
there's a question about slide. Do you want to share slides or should we just look at your screen?
So is there not a slide right here that you can see, or?
Yeah, it's kind of hard to see. If you could share your screen, that would be better, but I don't know if it's possible.
I'm sharing my screen. I'm sorry about that. Let me go ahead and double check. Oh, somehow that didn't happen. Okay. How about?
Yes.
Now? Sorry about that. Must have gotten disconnected at some point. Okay, so you should be able to see it now. Thanks. So
yes.
I also want to note that we had 2 of these so-called professional or project engineers, both PhD students, one in my research group, one from Sean's research group, that took elevated leadership status throughout the project. Really made things work when all of the PIs were way too busy, which is something we realized midway through the project. So what is the Subterranean Challenge? Well, the entire idea is that we can have distributed robotics for constrained long-term operation in austere environments, austere in pretty much every dimension that you could imagine. You know, communications limited because we're literally dealing with rock and concrete, perception limited because there's bad illumination, there's haze in the environment, there's dust. If you're flying or driving anything, dust gets picked up. And what we wanted to do, the idea of our team, was to deploy heterogeneous teams of robots that could work alongside a human operator, a single human operator in a communication constrained long-term operation in built and natural underground environments. And for us, you know, we were sort of playing to DARPA's fiddle, if you will, because they were the ones that sort of put forward the competition and said, you know, best teams can compete, and we're going to fund a few of them, and that's what enabled us to be able to operate. Here's a video that is sort of supposed to give you a feel of what a deployment of one of our robotic field deployments looks like. You can see that there's somewhere around 12 and 24 individuals involved. There's a number of different robotic platforms that have all been engineered by us. There was no second or third party that was doing this engineering. We were the ones that did this in collaboration with IRIS, which is an on-campus institute that supports these sorts of field operations. Was a real benefit to have them here at CU, capable of responding to our needs and being able to pay them to do that labor and equipment manufacturing as needed. The one human supervisor looking at the mission base station, as it's called, all these people in the field, that's just part of the test, right? I mean, in reality, when we're doing the final deployment for DARPA, we can't have people in the field. We can't even have people looking at the computer monitor, except for the one human operator. And I'll show a quick picture of what that looks like in a sec.
Wait, why is that?
That's part of the rules. They only wanted one human that was ever interacting with the entire system as it was in the environment. So that means that we could have a pit crew of 4 students or individuals that were working on the robot before it went in, but as soon as it was in, then
You didn't have miscellaneous people who had nothing to do with the project in the space along with the robot.
absolutely not.
Other
Yeah.
workers who were doing something else.
So in this competition, the field was completely cleared of all personnel, even DARPA personnel. And this is also helpful. So you can see our robotic team, right? There are 2 different types of robots that you probably noted already. One of them is a ClearPath Husky, which is a 4-wheeled vehicle. And then the other one is the Boston Dynamics Spot. We had 2 of each in the environment. And I'm going to talk a little bit about that platform choice in just a sec. So, this illumination is actually better than many cases in the environment. So we did bring cameras with lights attached to them along so that we could go and find things. That's the point of the competition, to find a fire extinguisher, find a drill, find a mannequin that's supposed to be a survivor, et cetera, these kinds of things. And so this is just a quick overview. All of this was put together in this Subterranean challenge in which 8 teams competed against one another for $3.5 million in total prizes. Happened just last month, I guess a month and a half ago. And if you are interested in watching more about this competition and what happened, we have the team's full competition run from minute 0 to minute 60, the 60-minute deployment, in this one YouTube video that DARPA's provided for us.
Is that a real city?
Beg your pardon?
Is that a real city?
A real city? No, I don't think so. That was on their website. Yeah.
It's not what happened.
Yeah, no. So, I mean, there's a lot of like footage like this in this video, in case you're, so like places where the robot has some really tense cases, tense things that happen. Also in this setup, you can see on the top how many minutes are remaining of a 60-minute run, how many active robots are in the scene. A score, that is a score of how many artifacts we found, how many of those objects of interest we found and properly located up to 5 meters accuracy according to DARPA's mapping server. Attempts, that's how many times we've thought we've seen something. So 9 of 25 in this case, so we're scoring pretty well. And the number of sectors explored. So the map was broken into these sectors with 3 different types of environments: tunnel, urban, and cave. And this nice little infographic shows, how we're doing in terms of mobility and autonomy into the environment. So this is just a kind of high-level view of how you can parse all the information that's coming at you here. And also, you can see as well in this kind of little bits of footage that I've given you what the environment looks like. This is a little bit of the urban environment before we saw a little bit of the tunnel environment where the robot was tripping a little bit on some of the dust and loose rubble there. And then cave environment, I don't know if we're gonna get to it here, but I'll show you. A cave is basically just large cavernous sort of spaces where the robots have to go and look in every single corner, and might be beneficial to have like a UAV or something. We only had ground robots in that case. All right, so a couple of quick photos of what this looked like. These are all photos from the final competition. And so there's a couple of photos of our platforms that you can sort of soak in. There's all the money we took home that's being basically pumped right back into our research labs as the ability for us to build more platforms, acquire more equipment, train more students and be able to support operations like this, or being able to ramp up for operations like this in the future. And let's see, so this is the final score right down here, which is the description of like how all these teams did. We're Team Marble, number 3 right down there. Cerberus was a team led by ETH Zurich and Norwegian Technical National University. CSIRO Data 61 was led out of CSIRO in Australia. It's a research organization in Australia. All right, so I just wanted to give you kind of the picture view of all this before we jumped into those 4 areas that I talked about. So first of all, let's have a brief conversation about mobility. So these environments are super challenging for being able to drive or operate robots in, is for hazards, as you saw previously. Talking specifically about our ability to build up platforms and what platforms we chose through the competition, I've given here this sort of timeline of how the platforms evolved as we deployed these robots in the different circuit events leading up to the final competition. So there were these other tunnel, urban, and cave specific events that were held. And as we started this project, we thought our team was largely going to be Huskies, parkour cars, small UAVs, and large UAVs. That's what we proposed to DARPA. Turns out that changed dramatically as the competition went on, mostly because UAVs are extremely difficult to operate in narrow, constrained passageways, especially with the dust that comes up and everything. We essentially de-scoped UAVs very early. And we did end up doing some more development on it later, which I'll talk about, but there were some reasons why we didn't end up fielding it in the final competition. We had a lot of modulation between platforms as the competition, as the 3 years of this competition went on. So we chose first a Husky and then this tiny platform. We noticed immediately that the tiny platform, this parkour car, would easily get high centered on anything that it ran into. And high centering in an environment like this is just disastrous. So you can't move the robot anymore. The wheels are useless. Now it's just basically a comms beacon that's sitting there, like a $50,000 comms beacon in the environment.
Can't you get one of the other robots in there
To bump it?
kick off?
Yeah, I mean, that would be great. But even then, systems engineering, like it's enormously complex to think about how these systems have to interact with anything like that. I love the idea that, how do you do that without throwing off a camera or, destroying your LiDAR or something in the process? So we de-scoped parkour car, and then, which was sort of a heartbreak for me, because that's kind of where my research lies, of small, agile, autonomous vehicles. We moved to other platforms. These were treaded platforms, the LT2 and the HD2. These we actually deployed them in urban and some of them in cave, and they got high centered on everything as well. So even with 6 inches of clearance and treads, you still can't go through any kind of environment like you'd want, and a curb will stop you, right? So you would think, well, can't you see a curb coming? Not if it's dark, not if you have low vantage points, not if you're coming at it from the side and you want to turn in place and all of a sudden you get stuck. So at urban, we did really poorly with these platforms, and we immediately noticed that one of our competitors had a spot, and so we ended up, acquiring this spot, which I'll talk about in just a sec. Yeah.
What happened to the Mars rover that we bought from another university?
Yeah, we never used them.
Okay.
So, we did everything we could to throw the kitchen sink at the platform problem, because it's surprising, platforms actually are the easiest solution to most problems. It's like, well, you should just buy the right platform and then you don't have to do control, right? You just have a compliant platform and then you can just run it over whatever you like. And it turns out that's why we ended up on Spot, which I'll show in a second. So tunnel circuit, here was our deployed platforms, our tiny little car with a radar sensor on the front and a 2D LiDAR. And obviously we took the keyboard and the monitor off when we were there, but this car is about this size. Worked really well for a comms relay, but then it would get stuck on basically anything you ran it into because of these huge boulders and everything else. So the answer for me, by the way, is we need flippable cars. That's my thinking. It's something that can just torque like crazy and can get itself out of anything. And then we used our tried and true Husky in this configuration with a bunch of different beacons on the back. These beacons get dropped and they provide extensibility in the comms network, which I'll explain in a second. Now, at the urban circuit, we said, okay, the Husky was great and the parkour car was not as great. So let's put more energy into the Husky and let's add something else that we think will solve the terrain problem, right? And like I said, this 6-inch clearance here under these tracks was still not enough. It got caught on multiple curves. These vehicles were gone within 15 minutes of the competition, of a 60-minute competition. That's why I titled this talk, Failure is Not an Option, because what happens when this thing fails? Nobody helps it. Game is over, right? You can't even see anything else. So it's just, you can't, this was a terrible choice. And yet our, Husky, we said, let's rig it up with new sensors. Let's give it a thermal camera, which we've never done before. Let's even be able to say launch stuff from it, like a UAV marsupial operations or something. And that ended up getting modified just a little bit in the next competition, where we said, let's go ahead and add like some more sensors onto the Husky is getting to be this monstrosity kind of thing with like D435s, Intel RealSense D435s, an ouster, a thermal camera. Now it has another camera at the top. It's on a pan tilt unit. It's moving around in order to look at things. This did not work in the end, right? I mean, like there was too much complexity. One thing failed and the entire system would fall apart. And the problem there was USB. So my answer to you is never use a USB sensor in a field robotics exercise. We changed that by going to GigE cameras in the next generation. And then we had a great UAV, which ended up flying in the environment and scoring no points, but really looking really sweet. So, okay, here is another element of Cave where we decided, okay, we're going to put a marsupial UAV. We're going to simplify our beacon design. We found out we never deploy more than 3 beacons. So why would we even support that? We reduced that packaging. We said, okay, GigE cameras now running on Ethernet. So if one camera goes down, then it doesn't like make other sensors go with it because it's a fully switched network. That's how GigE cameras work. And we basically replicated that onto the tracked HC2, thinking that in the Cave environment that would do better. It didn't. So we just completely bescoped it for the final event. This was our final team where we had, as you see, in the matter of only 4 months, built up an entirely new platform, the Spot. It only took us 4 months of lessons learned from 3 years of deployments to be able to build what was like 90 or 80% of our points. And what really did this, and I want to bring this home again, is like that we didn't have to think about little tiny pebbles or curves anymore. Like we didn't have to think about the 0.01% of obstacles that are really hard to build classifiers for in perception. We just let the Spot do everything. And it had this super fast feedback loops in the legs that was able to allow us to go up very steep terrain and go over all those bad other things. So, you know, we were very pleased with the final competition platforms, and very simple as well. So all it took was $70,000 of buying a Spot. Who knew? So let's talk about networking. So this is, many people don't think about communications in robotics. We think about, you know, Wi-Fi. We think about mesh networking or something like that. I'm just going to send something over Wi-Fi. One computer is going to be connected to another. If I'm really thinking about this from a simple perspective, then I'm like, I'm going to put an access point on one of them, and then I'm just going to route everything through that access point, right? So it's literally your like Linksys router sitting on top of your robot. People do this, right? There's nothing wrong with that. What we found was that that Linksys and other kinds of commodity routers with commodity firmware that's been loaded onto them were optimized for stable connections where a computer was largely not moving in the environment. You might think, really, how important is that? Well, when a robot turns around a corner and loses connection, and then another robot comes into connection or moves past that corner with it, that exchange might happen in 15 seconds, and it might take 2 minutes to regain connectivity. This is unacceptable to us, right? We can't take 2 minutes to be able to say, oh, by the way, what's something that you found in the last 15 seconds? And then, because then by that time, you may have lost your connection. Everything's ephemeral in this environment. So what we did was we used commodity hardware, but we actually built our own what's called layer 2 networking stack, or our ability to route packets using the commodity hardware. Firmware changes are included in this in order to say, you know, prioritize certain types of connections versus others, and included in that, look at faster reconnect times. So be able to reduce the amount of time it takes to do that reconnection. We built a system that was interoperable with ROS, so we could actually parse this network status at the lower layers using ROS. And we built our solution on top of this new company that's sort of spinning out, one of our only true industrial partners who gave us what they were working with and actually collaborated with us in order to load this firmware onto the robots. So things changed a lot from tunnel urban to final. And what you'll notice is that what we mostly moved away from was these really standard things that if you Google searched, how do I create a mesh network? The answer will come up as Batman. It's a long story of what that stands for, just like Marvel. But you know, Batman is this protocol that runs at that layer 2 that I was mentioning before, and replacing that with the company's our collaborators' solution and building on top of that our own transport layer called UDP mesh, which was a new way of moving away from how ROS does things, which is this master or multi-master architecture where you have multiple sort of registries of who to talk to and how to talk to them, to purely a broadcast based protocol. For the most part, that was the biggest change that we saw in this. And I think that this is going to be a pretty big game changer for field robotics going forward. And my former postdoc, Steve McGuire, is planning on publishing a lot of papers on this. So this is kind of like a logical view of how this works. Where does Meshmerize come into this? Just in case you're not familiar with this, typically, usually there's this Linux kernel, and then there's an Ethernet bridge that is connecting your Wi-Fi and your Ethernet connections. That's something that you might actually set up at like an in-home computer. You would say like bridge these two connections. I'm sure some of us have seen that before. This allowed us to have our Wi-Fi and Ethernet connections be merged, so that packages from the ouster, from our LiDAR, for instance, would be able to go to a different computer or on the same computer, but a different network interface. And then, but you can see that Meshmerize sort of drops in right on top of the physical layer for Wi-Fi. So that's sort of the replacement. It was like a kernel module, if you will, on the networking stack. This is a view of how things used to be if you decide to run with just regular old ROS1 at the top versus the bottom, where we can clearly see that no longer do all of these different sub-processes on the computers need to talk with one another. They actually just can basically throw these broadcast packets, these UDP packets over the Wi-Fi connection. And at the end, that gets deconflicted into the different nodes that are maybe processing on a different computer that might be on the same robot. We were very happy with this. I mean, what this allows us to do is get manual control to the robots pretty much throughout the course. So if something bad happened, like we lost perception, like somebody decided to throw a bunch of fog in front of our robots, the operator would still be able to teleop it. This is like hundreds of meters past multiple corners into the course using the beacon plus transport layer technology we developed. We were able to send telemetry back, get mapping data like this one map, which was our final map of the environment. And also the real like crazy advantage was be able to get first person video. So now not only can the individual, the operator, control the robot manually, but also look at the environment, which you would think maybe that's necessary for driving. Not necessarily. What it was more important for is scoring things like this. This is like one of the things we were supposed to be able to find. It's a vent in the environment. It's actually really hard for convolutional neural networks to be able to converge on training and detecting a vent like this because of the self-similar geometry and it's not very descriptive, this physically or visually descriptive. And a human can pick it up though. So that was like a case where we scored like a bunch of points, 9 additional artifacts as a result of adding first person view as a result of really strong comms. So that was a huge advantage. Okay, so let's move away from mobility. We talked about mobility, we talked about networking. Now I want to talk about something that's really near and dear to my heart, which is perception. Unfortunately, this is probably the place where we had some of our, what I would feel like our most mundane struggles. Like they were not the fun research types of problems, and I'll describe why in just a moment. So we had an evolution, as I mentioned, of like what the perception head looked like on our robots. And by that, I mean, first we started off in the tunnel environment, and we had this LiDAR with, so a 64 beam ouster, that's that crown looking thing on top. And then 4 cameras that were all depth cameras that were pointed in different directions in order for us to look at the ground, look ahead, and then look kind of to the sides. We believed in the tunnel environment, this would be able to find most artifacts, most of these objects we were interested in finding. That was true, and in the tunnel environment that did fairly well, which is why we placed well in the funnel, part of the reason why we placed well there. But what we found over time was that it wouldn't look up, right? I mean, we didn't want to add a 6th, 7th, 8th camera. At some point, you start running out of actually like how many ports you can plug into and the amount of data that your computer can consume from all these cameras. So what we decided to do was simplify things, right? Nice engineering term as an academic. We simplified things by putting a moving platform on top of our robot. Okay, so and that was this pan tilt unit, right? So the camera is supposed to be looking around the environment for things. And then, oh, by the way, we still need to have 2 cameras here because the camera can't look down far enough, right? So now we have 3, not 6. We added a thermal camera because we thought some artifacts could be found thermally, looking at their heat signatures. And we added some precision Leica prism mounts for being able to localize the robot against the origin of DARPA. As I mentioned before, this was an utter failure in my view. The reason why is because most of the time when the camera was moving, it was undergoing motion blur, which means that only when it's stationary can it actually take a picture. And by the way, the robot's moving, so now maybe 1 in 3 of those images are no longer useful. We could sync the 2, but these real sensors actually don't have external synchronization available for them. And so this was just like a bunch of blur most of the time. And then what happened was one time our pan tilt unit like died, which meant the camera was facing like this the entire time. Found nothing, right? So this was an utter horror for systems. What we solved this with was basically saying, okay, we can do some math on the field of view of the cameras. We've done a bunch of these competitions already. We know what views are more useful than others. The front-facing camera and then 2 side-facing cameras would help us in wider environments like the cave, right? Not in the tunnel environment that we were in before, but now like these more open areas. And we went to, we added some flash lidars onto them to be able to provide even higher resolution of terrain. That was sort of the final. I don't think we could have ended up with a better perception head in the end. That was a pretty good system.
Did you have to
There's a
provide the
quick
lighting,
picture.
or did they provide the lighting?
We did these 5-watt LEDs. on
Yeah,
it.
but was there lighting in the environment? No, it was dark.
Well, in the urban environment, there was lighting. In the cave, in the tunnel, it was very dark. Yeah. Which is another reason as to why we chose the LiDAR versus cameras for state estimation, which we'll talk about in a sec. Yeah.
So in the competition, to get points, you have to record what you found.
You had to actually say there's a fire extinguisher or a drill or a mannequin or something at this location.
Okay.
So you needed to do that in real time. You needed to communicate that back to the base.
Okay.
Yeah, and then communicate that to DARPA. Great question. Other questions?
Actually, what's the difference between a flash lidar and a normal lidar?
Yeah, so great question. A flash lidar basically is an image, a lidar image. A regular automotive grade lidar, which is what I typically call them, are rotating arrays of lasers, which provide you not an image, but a point cloud. That's the biggest difference. Of course, a depth image can be viewed as a point cloud, but there's no way to really view the automotive grade LiDAR as anything but like a panoramic depth image. And even then it has to be interpolated. So there's a pretty big difference between the two in terms of their angular and azimuth, or azimuth and elevation resolution. Like what is the resolution of this image? Yeah. Okay. So I'll mention really quickly, I did say that we had to align ourselves against this DARPA reference frame. We went through a couple of modifications for that. One of them was first using April tags. Who's used April tags before? Who likes using April tags? Yeah, hands immediately go down in the room, just in case. And the reason why is because April tags are useful for range, but they really are not good at understanding your relative position to the target. And so what this meant was that these targets were essentially useless for us for determining how we were aligned against the DARPA reference frame, not where we were positioned against it. So we moved from that to a new method for us, which was using essentially surveying grade equipment, using this Leica total station here. And we then put prisms on the robot and were able to identify, where is the robot down to millimeter level and 1/10 of a degree accuracy, using an IMU to identify the location of, or the direction of gravity. Using these components, we were able to align ourselves with DARPA's origin really well, which is, if you can think for a moment, really important if you need to tell them what the coordinates of things are in their reference frame, right? All right, let's talk about something a little bit more interesting, localization. So for those of you who don't know, my research is largely in perception, and localization and mapping is a component, like a core to that field, right? our first idea for going through this environment was the usage of visual inertial sensors. The camera, like what you probably see most camera data coming from, right? Like a monochrome camera image, and IMUs, which provide you short-term temporal, like spatiotemporal constraints on motion. Now, that's what we went into with, and what we saw was that this system would fail dramatically in the cave environment. This is a kind of a disappointment for us. The reason being, we had to bring our own lighting with us, and if we had a light that was focused directly on a wall, then basically the image becomes light and no light. It doesn't become texture, it doesn't become features that we can navigate against. So the image is immediately useless. And this really was good to learn early on, because what we figured out from that was that we need to get a LiDAR. Like, this was just a necessary solution to this problem. We put LiDARs on all of our robots. We got the most expensive LiDARs we could buy, $32,000 LiDARs. Sometimes we put 2 on a robot because we just figured this was not something that we could actually have fail in the middle of our operation, right? Because then again, you can't tell anybody where some artifact is. We moved first from a 2D solution of LiDAR inertial simultaneous localization and mapping to 3D. And then when we moved away from the software package we were using, which was called Cartographer at the time, to LEOSAM, which is a LiDAR inertial odometry system that's backed with GTSAM, which is a factor graph-based probabilistic inference system. So this is just like a top-level view of like these solutions immediately moved from research to like automotive 8 years ago to like the stuff that people want to put on cars and other robots today. Like this is still too new. This was an interesting evolution, in my opinion, right? I mean, first we thought our research solution was the thing, we should do that. And then we moved to like other people's research that we could build on and build like a really solid solution for published papers in, but that like industry still isn't adopting. But it's like, we see this as being where things should go, right? So in the end, I could say very happily, we're still at the state of the art, but not in the state of the art that we expected. So that's just something that I wanted to point out, kind of an interesting result. Prior to the sort of open world, we were building these semantic or building occupancy maps, something like Octomap, if you're familiar with it. These are called occupancy grid maps, or voxelized representations of the world. So if you were to take this environment and break it up into a bunch of cubes, then you could then say some cubes are filled and other cubes are unfilled. Unfilled space means you can operate through it. Filled space are obstacles, right? What we saw was that these kinds of OGMs, or occupancy grid maps again, are they don't really capture things that you need to know, like these rails in the bottom, or tiny little pebbles that might actually still screw up your system. So we needed to map traversability, not just occupancy. And in order to do that, we built a sequence of classifiers. These classifiers were both traditional and deep learning based. And what we did was we took geometric measurements like normal and curvature, and we fused it into the occupancy grid map that I talked about in order to identify this area right here, this area right here, this area right here is a risk to drive over. So don't drive over it if you can avoid it. This was given to our high level path planning algorithms to avoid these sorts of risky terrains. So this was really critical to being able to navigate in these sorts of environments. One last thing about terrain traversability was we also semantically mapped stairs. We used our own classifier for being able to determine where the normals of stairs were and these point clouds. And this was because if you see something like this and you're a robot and you're trying to figure out, is this traversable? Generally, your answer would be no, right? I mean, this is like a highly rigid, cornered surface. And there's no notion that this is something that actually leads up to anywhere in a robot's occupancy grid map world. For us, we can see semantically that this is a flight of stairs that is to be ascended, right? So we had to build our own sort of patch, if you will, on top of mapping to be able to say, okay, these stairs, we have to be able to go up them. We used this normal classification technique and fused these into the occupancy grid maps as well to be able to say, okay, in these urban environments, our platform can ascend the stairs. This is an OGM with the semantic labels attached to it and the regular OGM around it. And up here is the stair classifications only. And on the left are the points that have been identified to be stairs.
What are the size of the voxels?
These voxels, I think, were at 0.1 meter resolution. Yeah, something 0.2 maybe. So yeah, they're pretty big sized, right? They're too big to handle those rails and other kinds of small things. This was helpful because even though our Huskies can't go into stair mode, Huskies, no way, right? They're gonna fall over or whatever. The spots have actually a stair mode that is discrete for them. You put them in stair mode and they can climb stairs, even with a 30-pound backpack on them, as we found. So that was sort of our final solution, right? We were able to build up OGMs that had some semantic information on them, traversable, non-traversable stairs. And we were able to use this map in order to share across the different agents and tell them, let's say that there was a Husky that saw a flight of stairs. It could then add that horizon onto, like a planning horizon, onto a spots map and say, maybe you should go check this out. And that was what allowed us to really build out that teaming that was mentioned. Okay, two more things on perception. First of all, how did we identify artifacts? The system was actually fairly straightforward. This was a sequence of ROS nodes that we built out. First, taking images from the gigabit Ethernet cameras, churning them through YOLO, which had been accelerated using a particular type of data structure and firmware for the Xavier platform, NVIDIA Jetson Xavier platform, using YOLO, which is a convolutional neural network for being able to determine bounding boxes and classifications of objects in a scene. We took that information, fed it through to a localization system, which took the depth maps from our LiDAR, corresponded it to where the image was, and was able to get exactly the distance along a ray, and therefore the XYZ location of an artifact in the scene. We use this using our OGMs, actually. We used probabilistically fused depth maps, not just raw depth map information. And then we were able to sort of send that message along with other artifacts that were non-visual to a human supervisor using the first-person video to be able to confirm or deny whether or not that report was valid. What was interesting about this, just as a quick note, we were told that CMU, one of our biggest competitors, people that we really wanted to beat at this competition, they had a similar system as ours, but they tuned their system for false. They were fine with getting false positives. And so by the end of the competition, they had thousands of false positives that they had to work through in order to determine where the artifacts were, which they didn't think about like the human robot interaction side of this clearly. They just thought like an individual could go through all these reports, who cares? And we were like, no way. Like if you send 1,000 reports to the human's useless, right? And so they were sitting on probably more artifacts than we were because they explored 100% of the terrain of the environment, and they had great localization as well. But their artifact detection system was broken, and as a result, they didn't do as well. So anyway, I just want to give some note to that. And I promised you only two more things. So this is the last one on perception. Then I'll move on to autonomy. So MARBLE stands for multi-agent autonomy with radar-based localization for exploration. And here I am talking to you about LiDAR, right? And I talked to you about vision before. Where was radar? Well, DARPA paid for a lot of radar work. And we did not deploy radar, but you can see here that this is a radar scan. These are sequences of radar scans populating occupancy grid maps, similar to the ones that I showed you before, for quadrotors, for a quadrotor flight in an environment. You can see actually it's doing pretty well, right? Like you can see the rafters, those pipes above that, I think I'll show that sort of like pipes above the environment. You can see the floor as it's being sort of scanned in, and you can see a clear path for flight. There are some false positives here, places where there is no geometry, but it's being filled in regardless. But otherwise, like radar is doing pretty well. So, I mean, we were actually really pleased with where we got for radar, not just for OGMs, but also for state estimation. This is a purely radar inertial-based state estimator, no vision used at all. So we're just giving you the first-person view so you can visualize it. And here are the sparse radar returns and our learned filter using what's called PointNet, a 3D convolutional neural network that's able to, that was trained on LiDAR supervision for false and true radar returns. That is to say, we used LiDAR signals in order to train where there are actually reliable radar points in each scan. And this scan it's not great. I mean, there's still a lot of false positives coming in. So there's still more work to be done, but we were able to fly a quadrotor in the Aspen lab with only this. And in this environment, you can even see clearly corridors, walls, etc. So we were pretty pleased. This was a first of a kind effort, being able to do this radar inertial based state estimation with learned filters. And I think that we're going to see a lot more of that over time. On top of this, we also released a data set that just got submitted or accepted to IJR yesterday. That's on this particular work using synthetic aperture radar and sort of like the most raw of radar returns that you can get in order to build out accurate sort of object detection and hopefully for other people state estimation and lightweight autonomy and perception solutions, including our own lab as we move forward. Okay, so let's move on to autonomy and then I'll take questions. All right, so the autonomy stack had changed pretty dramatically as we were operating in it over these 3 years as well. So first we started with a Bezier curve-based trajectory optimizer. This ended up finding, as one does with optimization-based solutions, no solution too frequently, right? Which meant that we couldn't rely on some kind of like MPC trajectory-based optimization for these rough terrain environments. And we ended up moving towards a topological and graph-based approach where we would mark out, oh, here's a hallway that we're walking down, here's a junction, and then here's a large open space. Sort of semantically building up graphs and nodes. And then whenever we explored an area, we would say, okay, we explored it, we're going to close the node, right? It's no longer open. From that, we saw that there were tiny little places where our classification system for topological graphs were not performing as expected, places like small rooms off of main rooms and corners or behind an object. And so we moved from that to more of an occupancy grid mapping based approach. These approaches were directly on the OGMs that were collected in order to determine whether or not we had seen something with a camera. So we sort of thresholded things to certain distances and fields of view in order to say, yeah, something has been seen. So therefore, we can move on. We don't have to continue looking at it. This was just fine until this was mostly this, actually, as you can imagine, since this is operating on the full OGM of an environment and the OGMs are 0.3 meters in resolution, that means that by the time you're done with mapping the entire environment, you have millions of voxels that you're doing mapping over. This is not good. This is where sampling-based approaches really shine, right? Huge environments that do sampling over large spaces statistically. And that was our final approach that we took. This is a quick solution to our tunnel or heads-up view to our tunnel. This was actually really just fine. It worked really well. Like we scored 4th place at tunnel out of 9 teams. We beat like UPenn, we beat JPL. I mean, we did very well at tunnel. And so this was sort of like what we felt, okay, this was fine, but we knew it wouldn't work for cave. So that's why we had to adjust to the other kinds of OGM-based solutions, which I'll talk about in a second. So this was, the topology was corridors and junctions. You know, we couldn't really do kilometer-based, like I mentioned before. It couldn't do constrained passages. It didn't do wide open spaces very well. And that was just like, you know, we also came up with like our own very basic controller here saying like, you know, stay the same distance from either side type of thing for centering. It was kind of a basic solution. The urban underground was where we first introduced this OGM-based approach, which I mentioned. This allowed for, you know, complex layouts. We could allow for 3D OGMs. These 2D OGMs with this view here are just for visualization of where frontiers are. So the challenges we were trying to solve with this were constrained passages, adverse terrain such as curves and corridors and junctions are no longer valid because of these open space kinds of problems. And that's when we moved to this frontier view planning, which was that if there were these frontiers that were available, we might prioritize certain frontiers over others. We would enumerate the types of viewpoints that we could take in order to sort of solve the problem or explore these environments. And then we would span out an A-star-like map to how do we get to these different views, and we would sub-select based on which view was closest, weighted by how many views it would take to view it. So this was sort of biasing implicitly towards larger spaces. This solution did fine, but I wouldn't say that it was great. Meanwhile, what ended up being our true solution, the sampling-based approach, was being prototyped on our aerial vehicles. This allowed us to avoid thin obstacles as well as large obstacles using this sampling-based approach, using this imperfect path following method that's visualized here, basically just this sampling and path following approach by taking distances from the path and trying to minimize them. I just want to mention, even though we didn't field aerial vehicles in the end, they did very well. This was an aerial vehicle navigating inside of a warehouse with, small thin obstacles and larger obstacles below and above. And it was able to navigate this entire warehouse, I think, for about 20, 30 minutes until the battery died without running into anything, which we were pretty proud of, right? Unfortunately, most environments in the Subterranean challenge were not as forgiving as this one, so we didn't end up deploying. Okay, so we wanted to move in a different direction. We were able to use these different fast marching methods, sort of iterations on the previous frontier-based approach, but with certain speed ups, being able to, look at these maps that are being fused in from other agents, for instance, in merge map coordination. But it still didn't solve the constrained passage problem, which, as you may know, it's because we were sort of biasing towards those open spaces. There was a limited choice of paths. We didn't always get every path available to us to go through these tiny rooms, and it had no awareness of terrain, which is why we moved to graph-based planners. Graph-based planners are not new. I won't go into all the details of them, but I will say that some of the cool things we did about them were, we threw in this terrain solution, which I've already mentioned. We were able to do graph sharing, so we had multi-agent coordination using this, and also dynamic obstacle avoidance, which was basically, opening and closing edges of these graphs based on the transit of dynamic objects through these scenes, which was a problem. DARPA sort of threw stuff at us in the final competition and whatnot to make our lives hard. All right, and so that's basically the end of that. Let's see, so this was sort of a discussion on how we were able to extend this to the spot. So we were able to look at, from the UAV to this robot in particular, and also even to the Husky. We basically just snapped all of our nodes to to the ground, and then we projected up by a certain height, which was the height of the LiDAR to the from the ground. And then we were able to evaluate whether or not certain obstacles were traversable through this sample-based planner. This was, the sort of shoehorning of obstacles into a 3D map that would be non-traversable for our robots. And then the last thing that I'll mention about this is, this sample-based planner was really amazing because it had so many knobs to tune, right? So we could tune to go to higher or smaller areas like this one right here, smaller volume areas, larger volume areas, and be able to prioritize based on them. If we wanted to, say, find everything else in this environment first, then search the smaller places, then go to larger places, which wasn't something that we had in that bias that we implicitly put into our occupancy grid map based planning techniques. So to me, this was, continues to be a really great area of research for these sorts of explorations, and how we condition parameters on the planner, in the planner, on the environments that we want to send our robots into. All right, so with that, I think I'm gonna, just go to our takeaways. So we had some really like core lessons learned from the competition. And one of them is that mobility, like we knew this was going to be a problem from the beginning. How do we sub-select on all the platforms that are out there, the best platforms for our environment? What we found was that we could have done just as well at the tunnel circuit if we had used only spots. And we could have done just as well at the urban circuit if we used only spots. And we could have done just as well at the final if we used spots. Meanwhile, we had Huskies the entire time, and that was only because of platform availability and cost, right? Looking back, I think that legged robots are clearly the win. Like in built environments, in natural cave environments, we need to really, we need to move away from wheeled vehicles unless we start thinking dramatically different about how wheeled vehicles work, right? They need to be like maybe super overpowered. Maybe they need to be like flippable, like I mentioned, like something that can handle the terrain obstacles that just are game enders for these robots. And aerial vehicles, while great, we didn't field them because we just saw that spots were better. Like, why would we put another resource into aerial vehicles once we see that spots can do the job? Networking. So we had found that having a flexible networking layer, the best that you can provide really allows for adding data flows like those first-person views and being able to do artifact detection using the human supervisor. And it also leverages the human-robot interaction, right? So like the robots themselves were not as capable autonomously as with a human guiding them. To me, this just indicates that there's a lot of research that needs to be done in like where human-robot interaction fits with emergency response scenarios. Like we had found anecdotally that if we added another robot into our 4-robot team, then our overall system would perform worse. This was a surprise and definitely a gap, right? If we should be able to scale the human or the robots and their autonomy with the humans' ability to oversee them. And yet today, working for Amazon, I see that 4-to-1 teleop in something like this is actually really impressive, right? Because in many cases, 1-to-1 or 2-to-1 teleop is what you get. So 4-to-1 is actually, gold standard in many ways. I would say that we did pretty well. Why can't it be 5-to-1? Why can't it be 6-to-1? I think that those are questions that we should focus on, as not just as a community, but also as a person who's interested mostly in the autonomy stack. In perception, we saw that terrain analysis is still just very challenging, determining where the robot can move, which is why the mobility side is so important. If we can solve problems with mobility, we no longer need to focus engineering time on perception, right? And especially terrain analysis. So this is this really challenging problem that I think is also an area of future work. I think that there's a lot of opportunities for semantic labeling and reasoning. We started using it before it got really too complicated for these different environments, how diverse they were. I think that when we think about maps and maybe even localization, I would think that semantics has to play a greater part than it does today than the metric side. And finally, I want to say, I'm surprised and pleased to say that radar is finally approaching prime time as a state estimation system. And we've already seen some of that kind of bubble up in the research field in our community, more radar related publications coming up, different radar sensors, different techniques from classical to machine learning based and everything in between. But I think this is an exciting area. I'm excited time to be working here. The last thing that I'll mention is that autonomy should support the human supervisor. It shouldn't just be this like, go out and do your thing, right? Like we should be thinking about how the human interacts with the autonomy and how we can open the autonomy products and decision-making up to a human. And that is non-trivial. For me, not being an HRI expert at all, like I think that this is an exciting area of future work. And that we need the autonomy to only provide a level of robustness required such that the system can no longer be constantly being fixed by the human, it's being guided by the human. So now autonomy is a tool for the human to be able to search the environment rather than the tool where the human is just like fixing the problems or some other kind of post hoc repairs that may be required in the field. And there's a lot of like programmatic lessons learned I can provide, but this is my final slide. If you're interested in the programmatic lessons learned, I'll just keep this slide up. you know, like to me, there's management questions about how to manage large teams that are distributed like this with $1.5 million budgets annually. How do we do team management? How do we do software management? And you know, what does it mean to choose a research path and then have to pivot? Right? We did that many times in this project. So anyway, yeah, I will leave it here and take your questions. Thank you for listening.
Wow.
Yeah.
What do you think about Ross now after the exercise?
I think Ross is excellent.
Is
I
it
mean,
still-
yeah, I think it is. We saw modifications to Ross being necessary in the comm stack, like in that we did some real low-level tweaking in Ross node communication, inter-node operability. But besides that, Ross made our lives a lot easier in being able to prototype much more rapidly. And so we didn't have to worry about, you know, middleware kinds of anything. That was all
So
solid.
all these sensors in particular.
Yeah.
Visualization, the 3D data.
Yeah.
Yeah.
Yeah, we were really pleased with it.
There's a
Yeah.
question from the chat.
Sure. Question from the chat. Did the legged robots don't offer any wheel odometry? Does that make SLAM poor compared to the Husky? We didn't use wheel odometry at all in our state estimation pipeline. LiDAR is really good. Like, I think that, you know, our solution had 0.05% drift over time without loop closures. So you start adding in loop closures and you're basically like perfect odometry or perfect SLAM. And so that means odometry like would have even been a drawback, you know, integrating wheel odometry, for instance, into our system would have been a drawback. So yeah, we worked entirely on LiDAR inertial. Alessandra also has a question. What's up, Alessandra?
Hey, Chris, so you know, in my opinion on this, but what do you think was the single most important strength of your success?
You know, honestly, I think that so many problems that we ran into throughout this competition were organizational level, that it was our ability to find compromises and to have students drive decision-making and have everyone in the same room to quickly react to problems, know who owned a certain component and be able to sign off on changes, even to the last minute. These were the biggest advantages of our team. Like, you know, there are smart people on every team that was in that competition, but many of them were like, almost like different teams because they were on the same team, but they were doing different things and they were at different institutions. I think that, you know, our ability to bring to bear all of the individuals and the talent that we had was probably our biggest strength. I don't think that's a cop-out. I think that's the reality. You know, Syra did really well. They were only one team. They beat us.
Thank you.
Yep.
So you said that adding one more robot to make it 5 made it worse. So are you saying, is it that one person can't control that many? Is that the idea?
Yeah, so it's not even control, because control is like a one-to-one teleop operation. But yeah, it's basically that with the amount of stuff that we had loaded on the human supervisor, that adding another robot would have then meant that there was stuff not being checked. And there was enough of that where maybe like there was some fixing that the operator had to do, like, oh, these two paths should not be conflicting in this way. I'm going to manually deconflict. Or DARPA just filled this room with smoke. I need to actually teleop the robot through the room because nothing visually will work. Like, you know, these are places where that one robot that went really far into the scene would have just stopped. And so, yeah, that's what I mean by it. It's like our system would have performed worse.
So is the solution, is the solution to have better autonomy or to have better, I don't know, communication?
Yes. I mean, the reality to that is like, yes, we need better autonomy, right? But then we are not maximizing our human supervisor's workload. Like, you know, we literally just had an interface that we threw together using like RViz widgets. I mean, this was a joke. None of us knew what we were doing. And except for Dan, the one human supervisor who put a lot of insight into it, but we could have used more. And I think that there's a lot more, you know, that we left on the table as a result. We could have been, I think, second if we had more robots and, considered a little bit more carefully what our human was doing at all times. Yeah. Are there other questions? Okay. Yep. What about the robot-robot interaction? Could any additional agents aid in autonomous deconfliction? Yeah, and this goes to Christine's point, I think that there was more about the autonomy and teamwork that wasn't really fleshed out that we could do future work on. Maybe Carl and I can chat about that offline. There's definitely a lot more there. Yeah, I know we're out of time. So thanks everyone for listening. Yeah, talk to you later.
Thank you.